This is a short lecture describing a method called the beam propagation method. It's not really used a whole lot anymore, but this is a very good lesson in applying finite differences. It has some historical importance. It was applied some time ago when computers had less memory and could not run as large of problems. And you'll still find it in the nonlinear optics community. It's unique in the fact that it can model nonlinear things very easily, and it's still a frequency domain method. That's usually pretty difficult. I will give you a brief introduction in what the beam propagation method is, try to give you a picture for it. Then we're going to formulate it based on finite differences. There's multiple ways we could formulate this. It could be a completely Fourier space method, which will make sense later. It could be based on the FFT, but the one that has arisen to the greatest prominence in beam propagation methods is the finite difference beam propagation method. Oh, we could also use finite elements or method of moments, a lot of different things. Then we'll discuss some details of implementing the finite difference beam propagation method, and I'll quickly outline some alternative formulations or different twists and bells and whistles that you can build into the beam propagation method. So here's a very quick overview. Just like the finite difference frequency domain method, or even finite difference time domain method, we're going to have a large two-dimensional grid, divided up and picking cell sizes and all that, following all the same rules that we did for finite difference frequency domain. The difference is, in finite difference frequency domain, we would calculate the field across this entire grid in one step. It's that backward division. But in the beam propagation method, something a little bit different happens. We're going to go in and tell it what the field looks like in the first slice. Think of that as the source. Then from there, we calculate the field in the second slice. Given the field in the second slice, we'll calculate the field in the third slice. Given the field in the third slice, we'll calculate the fourth slice. And we iterate that all the way through. But notice we're calculating the fields here without any knowledge of what's going on the right-hand side of the grid. So if there are any objects out here that would reflect waves, clearly we can't know that on the left side of the grid. So the beam propagation method almost always ignores backward reflected waves. Now, that is fixable, and we'll talk about that later. But the real power of the beam propagation method comes in, and it's most efficient when you can ignore the backward reflected waves, and there's many devices where we can. We could have two waveguides in close proximity where they couple energy back and forth, and there's not really a strong backward scattered wave, and it's really good for things like that. So anytime we ignore the backward waves, anytime we can do that, the beam propagation method is really good. And as I mentioned, that's fixable, but we'll talk about that later on in this lecture. So the way I'm recording these slides, we're not going to be able to see this movie, but suffice to say we have a series of waveguide segments here, and we'll excite it with a Gaussian in this initial waveguide, and as it propagates through directional coupling, the energy jumps over to this other guide, and then jumps here, and essentially 100% of the energy comes out the other side. So modeling a coupled line filter like this is done really efficiently with beam propagation method because the backward reflected waves are not very significant here. So this next section now, we're going to go through the details of deriving the beam propagation method based on finite differences. So we'll call it the finite difference beam propagation method. So by now, this should be a very familiar starting point. Notice we start with Maxwell's curl equations expanded into a set of 6 equations. Also notice we're using a normalized grid, and we normalize our grid by multiplying by the free space wave number. Also notice the prime superscripts on the material properties, the epsilons and the mu's. We've potentially incorporated a PML. So with the PML incorporated, we have these little prime superscripts. But this lets us formulate our method without really taking into consideration the PML. These are just lost terms that we can build into our mu and epsilons and then go ahead and jump into the model. And so we can formulate our model without thinking about the PML. Rather than derive a three-dimensional beam propagation method, we're going to derive a two-dimensional beam propagation method. So we're going to assume that our device is uniform in some direction. We'll call that uniform direction y. We'll have x be the transverse dimension, and then z be the longitudinal direction. That's the main direction that the field is propagating through your device. So if we set all the y derivatives equal to 0 in our previous set of 6 Maxwell's equations, we get this set of Maxwell's equations. And as you might expect if you've been listening to previous lectures, when we set one of our spatial derivatives to 0, Maxwell's equations decouple into two distinct modes. One we'll call the E mode, and one we'll call the H mode. The reason we're going to call this the E mode is because we'll take these second two equations, solve them for hx and hz, substitute those expressions in to get rid of hx and hz up here, and what we're left is one wave equation in terms of Ey. And we'll do the same thing over here, and we'll have one wave equation left with just hy. So we'll call one the E mode and one the H mode. And that also removes the ambiguity of calling one TE and one TM, where we may not quite know what TE and TM means. So here's our first approximation. We're going to make what's called the slowly varying envelope approximation. Well, we have an amplitude term, which is still a function of z, and we have a phase term that is a function of z. What this tells us is that the field is moving along and does not change very rapidly in the direction that it's propagating. When it does not change rapidly, this is a pretty efficient way that we can express the field and helps simplify the math a little bit. So we have another expression for the H and another expression for the E. Well, so we go back to our Maxwell's equations we had on the previous slide where they decoupled into these two modes, E and H. And we're going to substitute in these slowly varying envelope approximations. When we do that, we end up here. So the E's and the H's have disappeared, and we get these Greek letters now for the magnetic field and for the electric fields. So these are now our Maxwell's equations, if you will, but just with the envelope terms. The exponentials have dropped off, they canceled, and we're just left now with Maxwell's equations with the envelope terms. Well, now we're going to jump straight from the differential equations to matrix form. And so to understand this, you maybe could go back and review our finite difference lecture and also Maxwell's equations on a Yee grid. But what we learned in those two lectures is how to go straight from an analytical differential equation to those differential equations in matrix form. We're essentially approximating all the derivatives with finite differences on a Yee grid, and then writing this equation for every single point in that grid. And when we do that, we write that large set of equations in matrix form, and it becomes this. But the utility of this form is that we can construct derivative operators very easily. We can construct diagonal operators very easily, and we can construct a rather complex differential equation very, very easily. But just by inspection, you can see the similarity between our analytical equations and our matrix equations. Notice we did not substitute our z derivative with a derivative operator. We're leaving that analytical. Also look that it has become an ordinary derivative. That's because we approximated our x derivative with a finite difference, so the only independent variable left is z. So we can write that now as an ordinary derivative. And the same story for the H mode. So let's look at the E mode equations. As I said, we're going to take these second two equations and solve them for hx and hz. So here now are our expressions for hx and hz. So we'll take these two expressions and we will substitute them back into the original equation, and we end up here after we've done the substitutions. We turn our crank and simplify a little bit, and now we have a matrix wave equation which has both a first and a second order derivative, and this will cause us problems and leads us to our next approximation. So to understand that approximation, let's look at two different cases. On the top, we have two plane waves traveling at a pretty good angle off of the z-axis. Z-axis here will be running left and right, and these are propagating at a pretty good angle. Notice how abruptly the field varies over here. It's the interference between these two waves. Well, if those angles become small, and for the most part these waves are traveling left to right, the spreading is much less abrupt over here. So this is sort of the pictorial justification of the approximation we're going to make on the next slide. And this is very, very typical for beam propagation methods. We're going to make a small angle approximation. Well, if the fields are not diverging rapidly, then they're not going to be changing rapidly in the z direction, which was also our assumption when we made the slowly varying envelope. So it's consistent with that. So if the field in the z direction is not changing very rapidly, then the second order derivative has to be a lot smaller than the first order derivative. The first order derivative tells us how much is changing. Second order derivative tells us how much the change is changing. Well, if it's really slow, well, the first order derivative will be small anyway, but the second order derivative will be even smaller. So we're going to drop that from our matrix wave equation, and now we have a matrix wave equation only with a first order derivative. So now we use our algebra crank and we essentially isolate that derivative on the left hand side, and here's our final form of our matrix wave equation. Now we approximate this derivative on the left hand side with a finite difference, an explicit finite difference, and that becomes this: our e sub y at the next slice minus e sub y in the slice we're talking about divided by the spacing. Now notice, if we're talking about a central finite difference here, this term will exist at the midpoint between those two slices. So if I didn't do anything on the right hand side, I would be talking about an e that either exists at I plus 1 or I, not at the midpoint, so that wouldn't be compatible. So what we have to do is take this product, a times e, and we'll average this. This is a times e in the I plus 1 slice, and a times e from the same slice. And if we average those two, we're essentially interpolating the a times e product at the midpoint between I and I plus 1. So this A matrix, it's a big square matrix, and it depends on all the material properties within the slice. So we're going to calculate an A for every slice through our grid. And it is from this equation that we'll derive an update equation. And we do that by solving this equation for the EY at I plus 1, the electric field in the next slice. This is the unknown, and we solve for it. So when we do that, here's what we get. Here's our expression for the electric field in the next slice based on the field in the previous slice. And notice that depends on this A matrix from the ith slice and also the A matrix in the I plus 1 slice. It also depends on the cell size in that longitudinal direction, delta Z. And another big deal here is it depends on the effective refractive index. Notice this method does not tell us the effective refractive index. We have to make a really good guess. And this is consistent with the slowly varying envelope approximation, or the fields not diverging very rapidly. Things are not changing very quickly in the z direction. So propagation is, for the most part, very smooth. There should be some way analytically we can determine what that average refractive index is. Now for waveguide problems, you'd go back to our waveguide lecture, and we have a way there of calculating the effective refractive index. If you have waves bouncing all over the place, you have to make a best guess as to the phase marching in the z direction. And at some point, this probably is not the best method to do that. Now let's step through some of the implementation details. And this is all wrapped up in the block diagram. So like all our other formulations, we have equations all over the place. So what actually happens? Well, in the beginning of your code, you'll define all your simulation parameters. Size of your devices, refractive indices, wavelength, the effective refractive index that we're guessing. Based on all that, you can calculate your grid and you can optimize it in terms of cell size. Then you can build your device on the grid. And it's up to this point, beam propagation method and finite difference frequency domain look the same. We know we're going to need derivative operators. In this case, we only need derivative operators in the x direction because we're only simulating 2D fields here. And we also need to know the electric field in that first plane or that first slice. So think of this as the source. And we could do plane waves, we could do guided modes, just about anything. We just calculate some field in that first slice, and hopefully that field is also a solution to Maxwell's equations. If it's not, then this method can behave kind of crazy. So now we're ready to head into the main loop where we iterate through all the slices or layers in our grid. And of course we just entered, we're not done. So we will extract the material properties from that first slice and form our diagonal permeability and permittivity matrices. Once we have that, we can calculate this A matrix because we'll have our diagonalized material matrices. We'll also have our derivative operators, which we calculated before we went into the loop. So we can calculate I for the first slice and I for the second slice. Then we'll calculate a matrix propagator, which will take the field from the ith slice up to the I+1 slice. So once we have this matrix propagator, then we just simply take the field from that first slice. So in this case, it's our source, and we multiply it by that matrix propagator, and we get the field in the second slice. So we go ahead and we'll store that in our grid. We go back in, and now we're in the second slice. We extract the material properties, we calculate the matrix propagator, and we propagate the field now to the third slice. And we keep repeating this over the grid until we calculate all the fields everywhere. And then once we're done and we know the fields everywhere, then just like finite difference frequency domain, we can post-process it any way we want to, calculate how much energy got through or whatever. So let's look at some bells and whistles and alternate formulations of beam propagation method. I think by far the most common one is the beam propagation method based on the fast Fourier transform. So we'll call this the FFT beam propagation method. It's slower but simpler. It's simpler to formulate and implement, not quite as accurate, and has some other troubles. But basically this is how it works. You'll take your field in the cross section, and so to propagate it, the first thing we'll do is we'll take an FFT. This really gives you the amplitudes of a plane wave spectrum in that layer. We can take that and we can propagate through plane waves through half of a cell. So this whole box here, if you will, is just one layer, one cell in our grid. So we'll do half of it in Fourier space. We FFT our field so we get the amplitudes of these. We'll propagate them at half of a cell. Then we inverse FFT. And now we have the real space fields. We have some distribution of refractive index or dielectric constant. And so we can modify the phase in that cross section consistent with how much phase it would accumulate propagating through these materials. Then we FFT back to Fourier space and we propagate them for the second half of the cell. So it really, you FFT the field, you incorporate the phase, you FFT the field, propagate at half a cell, inverse FFT, incorporate the phase, FFT back and propagate. Inverse FFT, incorporate phase, FFT, propagate. And that algorithm repeats all the way through your grid. There's also fixes to beam propagation method to make it wide angle. And to do this, the most popular way is something used called the Pade approximations. And it starts off with a recurrence formula for our derivatives. So remember, we had a wave equation before we made the small angle approximation, before we crossed off this term. So let's keep it. We can write this a little bit more compactly. We can come up with this A matrix, just call that A. And now this wave equation can be written this way, a bit more simply. Well, we can solve this for our first order derivative, and we get the first order derivative in terms of the function itself and this ratio, and there's another derivative operator in here. Well, so this gives us a recurrence relation to estimate this first order derivative, and as this integer m goes 0, 1, 2, 3, 4, 5, our estimate in that derivative operator improves and also gets more difficult to implement. So this is how it works. We'll set the -1 order derivative, if you will, to 0. So now we'll approximate our derivative with integer 0 instead of -1, and we write our recurrence, and here we have the derivative at -1, which we know is 0. When we set this to 0, our approximation of that derivative just becomes the numerator, and it reduces to this. Well, this is exactly what we did when we did the small angle approximation. So in fact, that's just a special case of using this recurrence formula. Well, now we have an expression for the first order derivative, the 0 order approximation. Now we can look at the next order approximation. We write our recurrence equation. Now we have a new expression with the 0 integer there, and if we work through the math, here's our next approximation. Well, we can keep doing this and keep deriving higher and higher order accurate Pade approximations. But notice what happens here. We end up with a numerator, which will eventually go a squared, there's an a cubed, and it keeps going. And the similar thing will happen in the denominator. So we have a polynomial in the numerator and the denominator, and we can talk about their orders. So the order of the numerator will be n, the numerator and the denominator will be d. So people talk about a Pade approximation that is of order nd, and they're really talking about the polynomials in the top and the bottom. So we're not going to talk a whole lot about how to apply the Pade approximation, and let's go to the next slide, and I'll justify why that is. There's another thing that we can do with the beam propagation method to make it bidirectional, and essentially we build in scattering matrices or transfer matrices like we did before. So borrowing from the previous slide and this slide, there's all kinds of fixes to the beam propagation method. We can make it wide angle to account for waves diverging very rapidly. We can make it bidirectional. We can fix it. But by the time you incorporate all these fixes, you suddenly have a very complex code. And at that point, in my opinion, I think we should just scrap beam propagation method altogether and use what's called the method of lines, which is essentially the fully rigorous version of beam propagation method. Method of lines is a semi-analytical method. It's something we'll talk about later. So in my opinion, if you're using beam propagation method, it really should be for problems that it's well suited to. So one-way problems where we can ignore the backward reflected waves. Also problems where we can make the small angle approximation, where the fields are not changing very abruptly as they propagate forward. If any of that doesn't hold, I personally think, especially today with nice powerful computers and lots of memory, we ought to just abandon the beam propagation method and use another technique like method of lines, rigorous coupled wave analysis, finite difference frequency domain. I think they just work a lot better. So that's the end of this lecture.